Hi everyone, we are a group of students from Bmkt 3453 Computer Simulation. So today we present our project titled Finite Element Analysis of Gravel Bike Frame. Our team include Mugilan Ravindran, Mazlan Nixon, Abdul Faris Aiman and Alishan Ryan. Finite Element Analysis or FEA is a powerful method to simulate how a bicycle frame behaves under different conditions, such as pedaling, hitting bump, or climbing. So it will help engineers improve the design, reduce the chance of failure, and save cost and time. So in this project, we apply FEA to analyze a gravel bike frame and explore how it performs in real-life loading situation. For the problem statement, gravel bike experience a wide range of load because they are used on mixed terrain. So this will make it so difficult to ensure that the frame safety, comfort and durability. So to solve this, we must study the mechanical behavior of the frame using FEA. Also focusing on stress distribution and deformation under realistic conditions. So our project has three main objectives. So first one is to investigate how the bike frame perform under various loading conditions like climbing, pedaling, bump and downhill riding. So the second one is to compare steel and aluminium material and identify which perform better. And lastly is to design a gravel bike frame and analyze stress, deformation and safety factor using FEA.
Assalamualaikum. My name is Abdul Faris Aiman. I will present my part of detailed review. So, FEA is Finite Element Analysis in Bicycle Frame Design. So, FEA break down complex bike frame geometry into small elements to calculate stress, strain, deformation, and fatigue life. Secondly is to help balance strength, stiffness, and weight reduction. So, FEA also identify critical stress points early to save time and cost of physical prototype. So there are four common frame material, which is steel, aluminium, carbon fiber, and titanium. So each material consists of each character, which is for steel, strong, durable, and good production. So if we use steel material for FEA, we focus on stress distribution and vibration damping. So for the aluminium, it's like stiff and prone to fatigue. Also, FEA focus to stress concentration and fatigue life. So for the carbon fiber, is high strength to weight, stiff and vibration damping. For FEA focus for carbon fiber is fiber orientation and filaments. For recent studies 2018-2015 emphasize the critical role of finite element analysis in bicycle frame design. The field is well established with consistent focus on material, which is aluminium, titanium, carbon fiber, and steel. Standard load type, static, dynamic, fatigue, and impact. And key optimization goals: stiffness, strength, and reduction. So use of the standard like ISO 42106 is widespread, supporting method and consistency. So recent trends aims at defining FEA application optimizing material specific challenge. Example, composite layups. And simulating more complex scenario, example dynamic impact. There is a shift toward tolerating design for specific use like road racing or mountain bike rather than developing new FEA method. So there are four common loading and non-loading conditions that we use. Firstly is static stand up or climbing. Secondly is steady stand pedaling. Third is road bump or vertical impact. Fourth is horizontal impact. for example, is Finite. Okay. So for methodology, we design the frame using SolidWorks and run simulation against this range. So we use two frame material, which is steel and aluminum, and test for loading scenario. So here is the 3D CAD model of the gravel bike frame we designed. This serves as the base geometry for our simulation. So for loading case, we test for scenario. Firstly, it's not riding. Secondly, it's climbing uphill at 30 degree. Third, riding downhill at 30 degree. For this, hitting a bump at the front wheel. So we use realistic force up to 250 kilogram and additional 19.6 Newton impact force for the bump scenario. So for parameter settings, we apply a detail mesh to divide the frame into smaller elements. This will improve the accuracy of the simulation images. So for the fixed point, choose 4 contact point. First contact point is on the bolt fork on the front. Secondly, on the handlebar on the front, and third contact point which is on the back. So for the case number 1, which is normal riding condition, so the value of this is 150 kilogram, which is equivalent to 2,452.5 Newton, representing a maximum load suitable for real scenario. For the fourth case, bump at front at force of 19.6 Newton was used to represent force from loading over the rock. So for the case number 2, which is climbing up in 30 degree, so same, we apply force on the front and the bar. So for the case number 3, which is riding downhill, same, which is negative 30 degree, same contact point, fixed spot, same fixed spot, but we apply on the different force, which is on the back. So this is loading condition for the case number 4. It's bump at the front, we apply on the seat.
Hello, my name is Mazlan Nixon. My metric number is B0922102231. Today, I will explain about the preliminary result, which is for our case, we are using two materials, which is steel and aluminum alloy. So I will explain about the case 1, which is normal riding condition. So the result from the answer simulation, the maximum deformation is 0.033461 millimeter on the seat, where it's happened in very small scale. It's indicate the structure is stiff and well designed. But for the case of stress, the material yield strength for steel is 250 megapascal. The result show that it's exceed the yield strength for steel, which is from the simulation result we got 263.44 megapascal. There is a risk of yielding on the small area of the seat. But for the safety factor, the minimum value is 0.94897, which is it's occur on the seat, where it's indicate high risk of failure, but it's ineligible as it is an extremely small area. For aluminum alloy, I will explain first about the total deformation. The highest value of total deformation from case 1, but the material we are using is aluminum alloy, which is 0.42874 millimeter occur on the breast near the back of the joint structure. But it still happen in the large scale of the back joint. The second is the stress. The maximum value in this structure using aluminum alloy as a material is 266.76 megapascal. It indicates the material being used in this structure will be not yield during this normal condition for aluminum alloy. And the safety factor is 1.0496. This means the maximum stress is equal to the material yield strength, so which is it will not deform unless in under extreme condition. Next is case 2, which is our bike will under condition climbing uphill using maximum load 250 kgs with angle negative 30 degrees. So I will explain about the total deformation. The highest deformation is the value 0.020447 millimeter occur on the upper breast of the back joint and sit on the climbing uphill condition. And the stress, it's from the simulation value we got 76.587 megapascal. It indicates the material being used in this structure will not yielding during the loading condition, which is uphill climbing. And then the safety factor is we got the value of 3.2643. Well, this is indicate the maximum stress experienced by the component is less than materials yielding. Thus, this design structure is suitable for this uphill condition. And next, we are explaining the case 2, but using different material, which is aluminum alloy. The value that we obtain from the total deformation is 0.058299 millimeter. On the upper braces is very small, but this one is indicate the structure is stiff and well designed. And then I will go for the stress value, where we got 76.354 megapascal. It indicates the material being used in this structure will not be yielding during the loading condition. And then lastly is the safety factor. And then in this case, we got 3.6671. Thus, this indicates the maximum stress experienced by the component, which is the upper breast, suitable for this loading condition. And then we are continuing to the case 3, which is downhill riding condition. In this case, we are using a load of 250 kgs with angle of 30 degrees. So, the total deformation value is 0.1443 millimeter on the front of the seat, which with the large scale. This indicate the structure is not stiff and well designed for downhill condition. And then I will explain about the stress, Bmkt stress, which is we know that steel is yielding on condition 250 megapascal, but the result show that it's exceed the yielding strength, which is from the obtained value on the front of the seat, which is 418.72 megapascal. There is a risk of yielding in front of the seat. And then the safety factor, we got 0.56706 indicates a high risk failure at the front of the seats, but is still negligible due to its small occurrence area. And then we are continuing to case 3 with different material, which is aluminum alloy. The maximum deformation value that we obtain from the simulation 0.48166 millimeter on the front of the seat with the large scale and the medium scale at the back joint. This one is indicate the structure is not stiff and well designed for the downhill condition, as it's shown that the result at the back joint, it still have the medium deformation on the back joint. And then we are continue to Bmkt stress. The value that we obtained using the aluminum alloy as the material is 418.72 megapascal. But as from the theory, the aluminum alloy will yielding on 425 megapascal. Thus, there is no risk that the material on this structure will be yielding. And then we continue to safety factor. we obtain the value of 0.64311. This indicates a high risk failure, but it's still ineligible due to a small area occurrence on the back joint and the front seats. And lastly, case number 4, sudden bump at front condition. We are using the same material, which is steel, and then force of 200 kg vertically downwards on the seat. But in this condition, we are using 19.613 impact force at the front of the handle. So I will explain about the value of total deformation. We obtain 0.033404 millimeter on the seat, but it's occur in very small scale. This indicates the structure is stiff and well designed for the sudden bump condition. And then we go to stress. We obtain for steel, we obtain the value of 262.01 megapascal. But as from the theory, we know that steel will deform on 250 megapascal. Thus, there is the risk of yielding at the front of the seat, since it's occurring at the front of the handle. And then we go to safety factor value. We obtain 0.95416, but it's indicated failure in front of the seat, in front of the handle, but it's still ineligible because its occurrence due to the small area. And then finally, for the case 4, we are using aluminum alloy, and we obtain the total deformation is 0.4311 millimeter at the back joint, but its occurrence very large scale. It indicates the structure at the back joint is not stiff and not suitable for sudden bump at the front. And then we will discuss about the stress. We obtain the value of 265.4 megapascal. From the theory, we know that aluminum alloy will deform under stress 425 megapascal. Thus, there is no risk of yielding for this condition, as we are using aluminum alloy as the material. And then finally, safety factor. We obtain the value of 1.055. This means the maximum stress is equal to the material's yielding stress. So it's really well suitable material for this structure. Thank you so much.
Greetings and good day everyone. My name is Mugilan Ravindran, matrix number B092210410433, and I will be explaining about the results comparison of our FEA analysis on a gravel bike frame. So in the slide we can see two tables. So the first table on the left is a compilation of the maximum values for total deformation as well as von Mises stress for both steel frame and also aluminum alloy frame. And on the right in the table we can see the minimum safety factor values for steel and aluminum alloy, and both the tables, the values are for 4 cases that we used in this project. So based on the FEA results, under these 4 riding conditions, which are normal riding, uphill climbing, going down the hill, as well as bump at front, we can see clear observations. Steel frame exhibit significantly lower total deformation across all scenarios, and it indicates that the steel structure is much stiffer and rigid. For example, during normal riding, the deformation in steel is only 0.033461 millimeters compared to 0.42874 millimeters in aluminium. And however, this increased stiffness comes at the cost of higher stress concentrations and often exceeding the steel's yield strength of 250 megapascal. So there is a risk of failure. And in 3 out of 4 scenarios, which are normal riding, downhill riding, and sudden bump, the von Mises stress in steel surpasses its yield limit, resulting in safety factors below 1. Sometimes as low as 0.59706 during downhill riding, as can be seen in the table. And this highlights a risk of material failure. And as for aluminum alloys, aluminum alloy frames, we can see that it shows higher deformation values up to 0.48166 millimeters when going downhill. And this indicates that aluminum alloy is much more flexible structure. While this may slightly affect the frame's responsiveness, it contributes to better energy absorption, which is beneficial for off-roading comfort, off-road riding comfort, as well as shock management, which is both crucial for gravel bike, as gravel bikes are used in various terrains and often bumpy terrains. Importantly, aluminum alloy consistently maintains von Mises stress values below its yield strength, which is 425 megapascal in all of the 4 cases, and even under the most severe conditions, which is downhill and sudden impact at front, aluminium does not yield, maintaining safety factors above 1, such as 1.055 during sudden bump. Additionally, during uphill climbing conditions, it highlights the superior performance of both materials, as stresses are far below the yield strength, with high safety factors well above 3. However, aluminium still shows better safety margins, for instance 3.6671 compared to steel's 3.2643, indicating more tolerance in design. This is during uphill climbing. Although steel offers greater stiffness, it suffers from critical stress failures in most real-world conditions. Aluminum alloy, while more deformable, it provides better overall durability and safety by avoiding yielding and maintaining acceptable stress levels. Therefore, aluminum alloy is a most suitable material for gravel bike frames, especially for varied terrains that involves downhill riding and vibration and sudden impacts common in gravel bike cycling. Its balance of strength, safety and shock absorption makes it the preferred choice for both performance and long-term reliability for a bicycle frame of gravel bike. And it is important to note that most of the safety factors value, the minimum values, often comprises of a small area, a very small area of this frame, which means the structure might not entirely fail, but instead there might be cracks or fractures in certain parts of the structure in which the safety factor is low in that area, and this can often be negligible. As per required by the assignment, it is important for us to identify the critical loading. So based on these results, we can see that the critical loading condition among these 4 loading conditions is downhill condition. This is identified as the most critical based on the safety factor results. This scenario produces the lowest safety factor for both materials at 0.59706 for steel and 0.643114 for aluminum alloy, and both of which are below the acceptable threshold of 1, which means the bicycle frame will fail. These low values indicate a high likelihood of structural failure, particularly at seat areas where stress concentration is the highest. And the steep angle and increased dynamic forces during downhill riding significantly increases the load on the frame, making it the most demanding condition. Therefore, in terms of design, safety and material selection, downhill loading must be treated as the critical case and given special attention in frame optimization to ensure rider safety and structural integrity of the bicycle frame. As a summary, finite element analysis FEA showed that the gravel bike frame behaves under different loads differently. Steel frames were stiffer but often exceeded their yield strength in demanding situations like impacts and downhill riding, making them less reliable. Aluminum alloy, although more flexible, stayed within the safe stress values and had better safety margins. So downhill riding was the most critical condition, as I've mentioned earlier, with the highest risk of failure for both materials, regardless aluminum or steel. Overall, aluminum alloy is the better choice for gravel bike frames because it balances strength, flexibility, and fatigue resistance. The study also shows how FEA is a valuable tool for improving designs and ensuring rider safety, not just in this case, but also many real-life applications. That's all from us. Thank you very much.